they taught us that water is a universal solvent. Please, who remembers this statement? Water is a universal solvent. I really remember in BEC was one famous question that used to come. Then they asked you to explain what. You remember that question, right?
Yeah.
Charlie, because I'm more behind, up to this age, you still remember the things you've learned in BEC. Charlie, system, no, you know, so never, never think that you are not good. You are very good, in fact, I want you to say it after me wherever you are. Don't unmute, but just say it after me. I am very good. Yeah, I am very smart. I have whatever it takes to make it. Yeah, yeah, I'm very good. I am never dull. Yes, and I'm very smart. I am not dull. I will build things and I will make things in Ghana. I will apply. These are things you should be telling yourself every day. Me, I tell myself these things every day. I wake up and I'm like, me, I would invent things in Ghana. They say you can't do these things in Ghana, but I will do them in Ghana. Yeah, just tell yourself every day. Just tell yourself every day. Never let doubt overcome you because you guys are so good. All right, great. So universal solvent. Water is a universal solvent because we say that it can dissolve most things. We won't say all things, but we can say most things. So the thing is this. So there are two ways here. We have solvent, something that dissolves or is able to melt something. Then there is another term which is universal. Universal. So there are two things here: solvent and universal. Now, the universal word here expresses the fact that it works with a lot of things. It dissolves a lot of things. So, similarly, in logic gates, we have certain gates. Now, I've already established to you that there are three fundamental gates: the AND, the OR, and the NOT. Okay. Then, in fact, I omitted two other gates, and I should have introduced it to you. Or let me say four other gates that are derived from these three. So you have the NAND, the NOR, then we have the XOR, and then we have the XNOR. So this brings the count to 7 logic gates. Now, it will interest you to note that NAND is when I'm combining an AND gate, then the output of the AND gate, I NOT it. This is called a NAND gate. So we can draw this like this. And that is a NAND gate. So this is called a NAND. So not AND. That's actually short for not AND. In fact, I've included all of these in your handout. I'm very sorry it has been late. A lot of distractions here and there. Then we have the NOR gate. So the NOR gate is like this. Not all, right? So we have, let's say we have A, B. Then the output of the NOR NOR OR gate is noted, so that this is equivalent to so we can say that both NAND and NOR are made up of two gates. So this one is made up of AND and NOT, and this one is made up of OR and NOT. Is Walid on the line? Walid.
Sir,
Okay, great. I told you've gone to
so
sleep.
Wally, you are not asleep.
Then Della, Della is not on the line. Okay. Please, I hope we all understand.
Yes, sir.
Great. This is very
Yes,
simple.
sir.
Very, very simple. Thank you. Thank you very much. So that is the O. That is the O. Please kindly mute the feedback. Someone is giving us feedback. Now, then we have two other gates that are very, very important. Very, very, very important. We call it the exclusive OR. The exclusive OR gate is OR gate that is exclusive. Exclusive means, so when we say inclusive, it includes something. But exclusive means it excludes something. Now, that something that we are relating to here is okay, so this is it. Exclusion, something that is not the same. Inclusion is something that is the same itself. That is the same, like it includes itself. It excludes itself, right? So the XOR happens when if we have two inputs, the output here is 0, 1, 0, 1, 0, 0, 1, 1. When the outputs are the same, it is 0. But when the outputs are not the same, it is 1. Very, very simple. So whenever the outputs are the same, it is 0. When the outputs are not the same, it is a 1. That is why we give it the term exclusive. It excludes itself, right? So that word exclusive comes because it excludes itself. So we call this the X or gate. The X or gate. In fact, is useful in many, 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 many ways. And the symbol looks like this. You're going to see it plenty places, and you need to take very good note of it. It's just the or sign like this. Two inputs here, then this exclusive or. How do you use the exclusive or? The exclusive or is used, for instance, when you are monitoring 2 bits, right? For instance, let's take this example. A certain system contains 2 identical circuits operating in parallel. As long as both are operating properly, the output of both circuits are always the same. But if one circuit fails, the output should trigger something to happen. And you see that is an exclusive or. Please, we understand. Please, do we get it?
Yes, sir.
Great. So the exclusive is very, very used. It's highly used in the industry. You will see it almost everywhere, right? Because it monitors when two things are out of sync, right? Whenever two things go out of sync, then the exclusive um, um, gate will automatically engage and then make sure that things are detected earlier on. So that is the exclusive or, and it's very, very important. Then we have the exclusive NOR, XNOR. XNOR. Now in the XNOR, let's first start from the not of the exclusive OR. Whenever you have an exclusive OR, if you not it, so the symbol for XOR is plus circled. And you have a plus sign and you circle it, that is the XOR. So the symbol for XNOR is plus circled B naught. Now, the formula for A plus B is equal to AB plus A dash B. So AB dash plus A dash B. That's a formula for exclusive OR. Then exclusive NOR is this, not. So 0, 0, 1, 1, 0, 1, 0, 1. When the inputs are the same, here should be 0, but here is going to be 1. Right? Then when the inputs are not the same, it should be 1, but here not, so it's going to be 0, 0, 1. So the XNOR is a direct opposite of the XOR, which is that it should trigger only when the inputs are the same. So when the inputs are the same, yes. When the inputs are not the same, no. So this is very good if you want to check 2 bits or 2 flags. Anytime you want to check 2 flags, 2 bits, you simply deploy an XOR. And then if you want to check if they are the same, that's an XNOR. If you want to check if they are different, then that will be XOR. If they are the same, it's the XNOR. If they are different, it's XOR. Please, do we understand?
Yes, sir.
Great. Now back to that concept of universal solvent that I was relating these gates to. But before we move on to that, let's try and draft the truth table for all of these. So let's draft the truth table for the NAND circuit. NAND, not AND. So we have A and B. Then we have the output. So we have 0, 1, 0, 1, 0, 0, 1, 1. So if it was the not, all of this will be 0, 0, 0, 1. But because it's not AND, so we will write the inverse of all of this. So this will be 1, 1, 1, 0. So let me clean the other ones. Okay. Then this is the NAND. Similarly, the NOR. The NOR, we have A, B, and then output 0, 1, 0, 1, 0, 0, 1, 1. If it's the OR, here will be 0, 1, 1, 1. But it's NOR, so the not of this. So this is going to be 1, 0, 0, 0. So let me clean the other one too. Here. Okay. Now, for comparison, let me write the truth table for OR to end. So OR, we have A, B, output 0, 1, 0 1 0 0 1 1. So this will be 0 1 1 1. Okay. Then let me draw for the last one. We are going to be comparing something soon. So let me draw for end. Then we are going to have A, B, output. So 0 1 0 1 0 0 1 1. So here is 0 0 0 1. What can you say about these four? They look similar. Observe these four truth tables well. They look similar, don't they?
Yes, they do.
They do.
Yeah. So what can you say about the relationship between these two tables?
So it's like one is the inverse of the other.
Yeah.
Uh-huh. So
They
which
are
one
all
is
the
the inverse
inverse
of?
of the others.
Okay. So which one? So there are two pairs, right?
Yes.
Uh-huh.
So
So
the
the end
NAND,
is the inverse of the NAND.
The what?
The end truth table
The and is the inverse of the
is the NAND.
the okay, so the and is the inverse of the NAND. That is true. Yes, as for that one, that is established. But if you look at it closely, you can see that NAND and OR has some. I don't
yeah,
know if you see what I'm saying.
yeah. One is the inverse of the other.
It's like, yes, the vertical inverse. So you see,
Yeah,
there are two kinds of inverse. Either is a horizontal inverse or a vertical inverse.
sure.
You can see that NAND is a mirror, is a vertical reflection of OR.
Or yes,
And then the NOR is a vertical reflection of what? And.
and yes,
Please, are you seeing it?
yes,
Yeah. These two things. So these two things are mirrors. Now, look at something closely. Let's look at something closely. Let me take, so we are taking these two guys, these two sets. Let's go down on them. Let's take A, B, then let's take NAND. Okay, so before we take NAND, let me take A bar, B bar. Then let me take NAND B. Then let me take A bar or B bar here. Now let's write this truth table. So B is the least. So let's start from B first. Walid, are you in class or you are asleep?
I'm here.
The last time Walid slept, and today me jina on the console. Remember, I wanted that 1 minute.
yeah.
Last time he slept in the Nepal, the air, when the crowd, try.
He's asleep. He's asleep.
The
Walida,
guy
Why
was
you
asleep.
don't sleep?
I am ready.
hey Walid,
So
He's asleep.
let's,
Walid asleep.
Why are you sleeping?
yeah, Walid, I am ready. So let's find A inverse. A inverse will be 1 1 0
zero
0. Then
zero
B inverse will be 1
zero
0
zero
1
one
0.
zero.
Now let's find A and B. So AB should be 0 by NAND, so it will be 1. Then this should be 0, but 1 1 0. Now let's find A bar, this one here, A bar here, or B bar, 1 or 1 1 1 or 0 1 0 or 1 1 0 0 0. Are you seeing it?
Yes, sir.
So we can say that the NAND gate, that's the beautiful thing about these two guys, and it's very, very important I draw your attention to this. If I have let's have NAND gates here like this, then let's say I have two signal lines. This one is A, this one is B, then this one goes like this outside. It is the same thing. The output from this is the same thing as if I have an OR gate and I take the input from A, I note it before I take it into, because you remember De Morgan's law that states that A dot B is equal to A bar plus what? B bar. Please, do we understand?
Yes, sir.
Great. So similarly, if we take the NOR gate, if we take the NOR gate, which is A plus B bar, will be equal to A bar dot what? B bar. So you can see that if we come to these truth tables too, we can say that this NOR and these guys have something in common. Please, do we understand? Hello.
Yes, sir.
Please,
Yes,
do we
yes, we understand.
Great.
Yes, sir.
Great. So that's the behavior of the NAND gate. Now, these two behavior of NAND and NOR, you see that right now NAND is equivalent to, or NAND is forming an OR gate for us, and then NOR is forming an AND gate for us. So we call these two gates universal. So the two gates which are NAND and NOR, they are universal gates. Because from any one of these, from NAND alone, you can form all the other 7 gates. So there are 7 major gates that we have. So you can use NAND alone to form all the other 7 gates. You can use NAND to implement AND. Right. So let's take NAND and see how we can use it to implement AND. So NAND, let's take NAND here. Number 1, let's implement the AND gate. So if we want the AND gate, if we have our inputs, this one is noted naturally. All we need is to note it again. So here AB. Over here we are going to get A, B note. Then after this note we will get A, B note note. So that we have AB, and that's an AND gate. Let's say we want to get an OR gate from a NAND. Let's say we want to get an OR gate from a NAND. But then let me not go to all first. Let me do the inversion. Let's say you want to get a NOT gate from a NAND. It's very simple. We have this NAND here. This AND gate here. Then we have a signal A. We want to find A naught. What do? We just tie all the signals together and give it to A. And we are going to have A naught here using one NAND gate. Now, if we want to implement the OR gate, what do? Let's say we want to get A or B using a NAND gate. We have our NAND gate here. We can give A here. Then this one alone will be B. Then we will feed it into another, NAND. So look at what happens. Here we have A at the input. At the output, you are going to get A naught. Here we are going to get B naught. Then we are going to get B naught, A naught coming into AND, right? So we are going to get here A naught and B naught all knotted. Then we apply De Morgan's and we are going to get A naught naught plus B naught naught, which is equal to A plus B. So from one AND gate, we can use from one NAND gate, we can use the NAND gate to implement the AND gate, the NOT gate, the OR gate. If you want to use it to even implement XOR, we can still use it. If you want to implement XNOR, we can use it from just one NAND. You can't do the same with any of the other gates. You can't do the same with AND gate. You can't do the same with OR gate. You can't do the same with the NOT gate. But if you have only one NAND gate, you can implement it. You can get all the other gates from just that one single gate. Please, do we understand?
Yes, sir.
Great. So we call the NAND gate universal. The NOR gate to exactly the same thing. In fact, the NOR gate, you can use it to do exactly the same that you would use a NAND gate for. It's exactly the same. There are no differences between these two. So we call these two gates the universal gate. Now, why is this important? This is important because let's say I want to design a component, a logic. Now, imagine that the logic is complex, and so I have to use a combination of AND gates, OR gates, and NOT gates. So I have to manufacture a lot of all of these different components. I manufacture some AND gates. I know that over here I need 3 AND gates, I need 4 OR gates, I need maybe 10 NOT gates, so that I'll put it together and manufacture this logic. It becomes complex. But imagine that all these gates I need, I can implement them from one. I can just implement them from only one logic. Now, all that time that I will have wasted to manufacture all these different ones, I will just have to synchronize it and manufacture only the NAND gate. Then I don't need to do the rest, because from this one NAND gate, I can get all the other ICs that I should have taken that time and manufacture. So if you go to the industry, people don't manufacture AND gates. In fact, it's very difficult to get these individual gates to buy. But on the market, you find a lot of these AND gates there, because from AND gate, you can get every other gate that you are looking for. Or from the NOR gate, you can get every other gate you are looking for. Please, we understand.
Yes.
Great. Now, the other advantage of this is that if I make a circuit, let's say I make a microcontroller, we call these FPGAs, right? Which I am ordering one for you in your kits. Now, in the FPGAs, what we do is that we put a lot of NAND gates. Every NAND also is made up of NAND gates. Some are made up of NOR gates, depending on what you do. But mostly in the industry, because NAND always goes along with the sum of product, SOP, which is easy to implement. Most of the FPGAs are all made up of NAND gates. Now, when we give you this FPGA, which is made up of a lot of NAND gates, your task will be to make the connections, write the connections together so you can develop your circuit. And when you develop the circuit, you're like, okay, this line must go here, this must go here, then we connect the circuit together. In the FPGA, you don't need to manually build that circuit. All you need to do is to get the FPGA, which is made up of a lot of NAND gate in it. Then you would write the circuit that you want to make contact with each other. You program it into the FPGA and it can implement any logic that you want to build. So if you get one FPGA, you can implement any logic in your mind that you want to use these logic gates to build. And it makes development very, very easy. So in the industry, I've told you that industry hardly relies on microcontrollers unless they must do some processing. But apart from that, because of reliability and simplicity, to reduce complexity, we easily rely on, logic gates. And so most of the industrial components you'll be dealing with will all be FPGAs. And so if you know how to program them, it's an added advantage for you. So as part of the course, I'm importing one easily accessible FPGA that you would be playing with. You'll be learning how to program and write the codes onto it to make the connections using the NAND gate and the NOR gate so that you can understand how these things work. Please, is that right?
Yes, sir.
Great. Any question before I move on? Okay, great. Now, let's quickly move on to the K map, the Karnaugh map. Then let's close that chapter for today. Let's take this example. In fact, I allowed my TA to come and take you through it, the electrical B, but I learned that you didn't solve a lot of questions. I was expecting that you solve about 5 different questions because you need to really understand the Karnaugh map. The rest of the course depends on it. So let's take some time and then solve some Karnaugh map and understand these things. Now, let's take a practical problem. Very, very practical problem. Where is the question? Okay, so we have a borehole pump serving a rural community in the Bono region. So we are designing a controller for a borehole pump. So this is how your exams is going to be. Enkoye, what is every what is the then? What is the mochum hole? What is every.
Hey, say a bewu.
It will see
A bewu say.
ask yourself, said, how will I apply this? Then be applying it yourself before you come to your midterm and your exams. Because it's not going to be what is. Unko di baba biya metre what is. Momo pe baba too much. Mudi baba na mo aye check o ye kasa mo kra. Pese baba no re be free.
Sarah wanted to say
Di esesa nneɛma no. Saa ne yɛde atete mu nti esesa nneɛma kakra. Esi esesa mu. As I yes, Jimmy Mobra. Albert Einstein said something. He said, if you continue doing what you're doing, don't expect to get a different results. So if you don't like the results if you don't like the results you're seeing, you need to change what you're doing. And yeah, mention messi some because I don't like the results I'm seeing. You shouldn't be an electrical engineer. We are electrical and electronic. In your electrical and electronic come. The electronic knows also you powers. Eh, fufuru po apart from pool fufuru they win you at that thing be a bit. Go industry and yeah the more ye menial jobs so embarrassing. So we need to up our game and then change the status
So
quo.
the mission will be more of calculation.
Oh, it will be more of practical. Like all the questions will be practical. All the questions will be practical. Like this kind of question that I'm giving you. Let me even once you can share. Let me just copy it and then share. So copy. Oh, let me screenshot it instead. So a borehole pump is serving a rural community in the Bono region. So we are designing a controller to protect the pump. You see that if I ask you to design a controller, I won't say and I say Arduino, yankoto Arduino, Debbie. Pacho. Yankoto Arduino. Yankoto Arduino, bra. Uti Arduino, no one tell the go be IBM, Pacho Debbie. Yes. So yankoto Arduino be our. Now, the pump has yes, okay, so it has 3 binary condition inputs. W is equal to 1 if the water level is okay. P is equal to 1 if the pump motor is not overheating. V is equal to 1 if voltage supply is within range. I hope you agree to all of these parameters. This is how we protect a motor, isn't it?
Yes, sir.
Yes. Because if the water level is not okay and there is no water, it will be pumping air and it will get hot and then get bent. So the pump will just get bent. You have to buy another pump. So water level must be okay. And P is equal to 1. That means the pump must not be overheating. It must not be hot. Then V is equal to 1. Voltage supply is within range. If we have an over voltage or under voltage, we don't need to run the pump. It will destroy the windings. You've done electrical machines, so you know this. It will destroy the windings. So we don't have to run the pump. So the pump must only run if at least 2 of the 3 conditions are satisfied. Now, this is why we are saying at least 2. If water level is not okay, so let's say that at least 2. So that is when water level is okay and then pump is not overheating. That one is a good condition. We like it. Then water voltage rating is within range and pump. So let's write all the conditions that can happen. So we said at least 2 must be okay. So at least 2 must be okay. Water level would be okay. So water level will be okay. Then pump will be okay. Or water level is okay and the voltage is okay. Right? Then we would have pump is okay and voltage is okay. Then okay, so these will be the 3 conditions. Is that right? Please, we understand.
Yes, sir.
Because we are saying at least two. If at least two of the three conditions are satisfied, then at any point in time, at least two. So it can be either this or this or this. Now, you may be asking, oh, sir, but if, let's take the third condition here. If the motor is not overheating and the voltage is within range, what if water level is not okay? Won't it destroy the fan, the pump? That's a very brilliant question if you're asking it. Because we've said that two, at least two must be okay. If the water level goes down, the moment water level goes down, the pump will start overheating. So even if we don't see the water level is down at that point and we feel the pump is overheating, it needs to turn off. Please, we understand.
Yes, sir.
So the conditions are inclusive, they are interdependent, right? Now, if you say water level is okay and voltage supply is okay, you're like, okay, say, yeah, but that is what we like. So each of these three conditions are interlinked. Let's see how we can use the Karnaugh map to simplify this. Now, the question is that we are to number one, we are to find its truth table. Then number two, we are to simplify the equation, the logic, simplify the logic. This example, I'm taking it from your handout, so it's in your handout. So I just lifted it directly from your handout. So how do we do this? So we have three variables, W, P, and V. So let's W, P, and V output. So V, P, W. Please, this order is very important. Don't miss them. Don't miss them at all. Then let me call this M number for the main term. Look at here what we have. So as usual, these areas are going to be our favorite order 0, 1, 0, 1, 0, 1, 0, 1. Then our P is going to be 0, 0, 1, 1, 0, 0, 1, 1. Our W 0, 0, 0, 0, 1, 1, 1, 1. Then here will be M naught, M1, M2, M3, M4, M5, M6, M7. Now, this is where it gets interesting in you forming a truth table, because in the exams I will ask you and you have to do it. Look at what happens here. We said the condition is this. If the pump should run, that's the output of the pump is 1. That means it should run. Only if at least two of the three conditions are satisfied. So let's come to the truth table. When are at least two, right, satisfied, look at the M and tell me which of the M's meet that condition. Does
M6.
M6 meet that condition? So here is 1.
M3.
M3,
M3 meets that condition 1.
M5,
M5 meets that condition 1.
and M7.
And M7 because it says at least.
3 or 2.
So that means 2 or 3. Is that right?
Yes, sir.
Great.
M4 is not part.
M.
Okay, continue here.
Great. So 1, 2, 3, 4. All right. These 4 meet that condition. So this is part A and you are done. You just get your marks if you're able to do this. Now the next part is that after you've gotten this, we are to simplify the logic, but then let's try and write the output for run. So run or R into bracket W PV would be equivalent to the sum of the main terms M3, M4, sorry, M5, M6, M7,
Yes, sir.
which is equivalent to, yes, what will be the equation for M3? M3 will be what? What will be the expression for M3?
W prime PV.
It will be W bar
PV
PV plus
plus
M5 will be what?
W
W
prime
P prime
prime.
V, right?
Yes, sir.
Then M6 will be
W
W,
P prime
M6 will be WP
P prime
V prime plus
W
WPV. Okay, great. So this would be the equation for run. Okay, now we have to simplify this using the Karnaugh map B. So we are asked to simplify this using the Karnaugh map. So how do we do it? In simplifying this using the Karnaugh map, you first of all have to draw the gray code. Please, I hope you remember. I've taught you this, right?
Yes, sir.
Great. So you draw this box like this, like this, like this, like this. And here will be WPV. Then yes, 0, 0,
10.
I'm coming. 0, 0.
01
0, 1,
11
1, 1,
10.
1, 0. Then here will be 0
One.
and 1. Okay. So 0, W bar PV. W bar PV. So we are looking at W bar, which is here 0, and then PV 1, 1. Is that right?
Yes, sir.
Please, do we understand?
No, sir.
0, 1, 1. So here 0, 1, 1. Please, do we understand?
No, we don't understand. No.
Okay.
No, sir. No, sir.
Okay. So
Say
you take,
the WPV table.
but you understand the table I've drawn.
Yeah, the first one we understand it.
Okay, but where we are putting the values is what you don't understand.
Yes.
Yeah.
Okay, so let's go back there. So M3 is here. M3 says that W is 0, so we come to 0. W 0 is here. Then P and V is 1, 1. So 0, 1, 1. Here's 1, 1. So here. You understand?
Yes, sir.
Then M5. M5 is here. And M5 is W is 1, 0, 1. So here is 1. So 1, 0, 1 will be here.
Okay.
Then M6, 1, 1, 0. So 1, 1, 0 is here. Then M7, 1, 1, 1. So 1, 1, 1 is here. Is that right? Okay, so great. That's a Karnaugh map for you. Now, when you're able to do this, the next thing in Karnaugh map is what we call groupings. So a rule of thumb is this. If you have a 3-variable Karnaugh map, it means you can group in powers of 2s. 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3. So you can group in 1, 2, 4, 8. So over here, I don't want to see that in the exams, somebody has gone and is grouping by 3. Then he say this, no group with 3. So we don't group by 3. We group by either you are grouping them in 2s, in 1s, in 4s, or in 8. So we group 2 like this. Then here we can group another 2 like this. Then here we can group these 2 like this. Please, we understand.
Yes, sir.
Great. Now, let's take each of these groups. So when we take this group here, this one, you look at it, W column is not changing. But then the P column too is not changing because P, this is P, is 1, 1 here. But V is changing from 1 to 0. That means V will go. Please, we understand.
No, sir.
So the Karnaugh map, that's what it does. It looks at which one is changing and which one is fixed. So you look at this side here, W is fixed. W is not changing. But then when you look at the top one here, like this,
Yeah, that is
you can see that the P value here
yeah. Okay.
is 1 and the P value here too is what? 1. It's not changing. So that one is still there. But you take the V value and the V value is changing. The V value here is 1. The V value here is 0. So the moment something changes from 1 to 0 or 0 to 1, it's deleted, it's gone. Please, do we understand?
Yes, sir.
Great. So if you look at it, you can see that the W is fixed. So W doesn't change. But then V changes from 1 to 0, so it's deleted, and P changes, P stays at P. So it becomes only WP. Then we will take this one. Now when we take this one, which one is changing and which one is not changing? Which one is changing from 0 to 1 or 1 to 0? Walid.
So Walid is
Walid is asleep.
Sir, I'm here.
Walid. So if you look at the middle one here, this one, which one is changing from which of the literals, the inputs, W, P, and V, which one is changing from 0 to 1? And which ones are not changing? Walid.
Valid one that.
Walid, don't make Anjams on network in Yajuma. And every day network be a so gone. So you can't tell me say network.
Valid was shut down.
I shut down. Walid, please, today you have the floor. We are recording this for you. You record what to YouTube. One kasa will be able to own our my delay. Okay, great. Well, at least you feel me. Me zoom in feel. Me share no backstage. Okay. Yes, please. Who else can help us? Which of the values is changing on that middle row? Which one is changing?
It's a W.
W is changing, right? So you see W changes from 0 to 1. From 0 here to 1. So W changes. But P and V, do they change in values?
No, sir.
No. So what will it be if you are simplifying it? What will it be?
It will be P, V, or prime.
PV, Y prime. You see that they are 1, 1. So that means they are positive. So there is no prime. Prime will come when it's 0.
Okay, sir.
Is that right? PV.
Yes, sir.
Okay. Great. Then the last one. What would the last one be? The last one, look at it carefully. Which literal is changing? W, P, and V. Which literal is changing?
P.
Which one is changing? Yes.
P.
P changes from 0 to 1. So P will be cleared. Excellent. Then what will be the final form? Yes.
W, V.
W, V. Please, do we understand?
Yes, sir. Yes, sir.
Hey, Adiwe, who here? Man, it will come back and bite you. So please pay attention and understand it well. So here we are going to say that R is equal to WV plus PV plus WP. So what that means is that this long equation here can be implemented with this simple logic. WV plus PV plus WP. Please, we understand.
Yes, sir.
Yes, sir.
So it means that it saves us. We have 1 NOT gate here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now it takes, so here is like 14 gate. We take it from 14 to 1, 2, 3, 4, 5. But I'm not counting it well. So yeah, but I hope we get the whole thing here. We get the whole concept.
Yes, sir.
Are you sure you really understand this?
So we are not sure.
Which part don't you understand?
Yeah.
Second table now.
Come again.
The second table.
The Karnaugh map.
Yes.
Okay, so let me go over it again.
Yes, sir.
Let me go over. Let me just draw the Karnaugh map again. Then we can. So let me clean this. Hey, wait, and I'm missing my weird Karnaugh map. No?
Okay.
So I was just there and it was dawning on me that no, you haven't finished. They don't understand Karnaugh map.
And
See,
it's very necessary.
yeah, good teachers will always know when their students don't understand.
Yeah.
When I come to class, I feel your energies. I'm like, oh no, my students are lost. They are in the bush. I need to go and bring them home. Yeah. Okay, so let's do it again. Now I start from drawing the Karnaugh map. So this is called a 3-variable Karnaugh map. And it's very, very, very important that you know it. So you need to know how to draw it. When you have a 3-variable, there is a way you draw it. When you have a 4-variable, there is a way you draw it. So 3-variable, draw it this way. Then the most significant bits come here. W. Then the next and the following ones go. So after we get that one, then we'll write the gray code on top there. So 0, 0, 0, 1, 1, 1, 1, 0. Please memorize these, or just know that we call it the gray code. One bit must change. It's only one bit that must change when we move from one place to the other. So 0, 0, 0, 1, 1, 1, 1, 0. Then we have 0 and then 1. Then now we will come and then pick each of these main terms and put them in it. Pick each of these main terms and put them in it. So M3, which is over here, right, is made up of W is 0, P is 1, V is 1. So W is 0, P is 1, so P1, V is 1, right? So it intersects here, so here and here. Is that right? Please, those of you that don't understand, I'm particularly interested in you guys, so kindly talk for me.
Yes, sir. Please repeat.
Great.
Yes, sir.
So, yes. So for the M3 is W is 0, which is this one here. Then P is 1 and V is 1. Right, so P is 1, V is 1. So 0, 1, 1. So here, you take this place. Then M5. We have W is 1, P is 0, V is 1. So W1, 0, 1. So W is 1, 1, 0, 1. So 0, 1. Then we take this place. This is where they all meet.
Okay.
Then we have M6, which is 1, 1, 0. So 1 is here, then 1, 0 is here.
Oh, okay.
So we are going to take this box. 1, 1, 0. Then we have 1, 1, 1 for M7. 1, 1, 1. And this becomes 1, 1, 1 over here.
Yes, sir.
Do you understand?
Yes, sir.
Great.
Yes, sir. Yes, sir.
Then when you form these, you will start grouping them. It's either you are grouping them as 1, 2, 4, or 8. You don't group them as 3s. If you group them as 3s, you are very wrong. I don't even know how you can solve it if you are able to magically group them as 3s. Some of you are magicians.
Like me, sir.
Magical.
Yes, sir. Walid is a magician.
Walid is a magician.
John, you are a magician, bro.
Walid Wadao.
Walid the magician also died. Also died.
Walid they do
Why
have
you go na ya nka wakasa dada.
Oh, Bob
Walid is
no.
Bob
Walid,
Bible.
say something. Say something.
Walid,
That is
say
close.
something.
Wada. Wadi dada.
I'm active.
Munja,
Hey,
what you got?
active.
Dada
I
is
so
here.
active.
Yeah.
Okay, great. So you are just going to circle them 2, 2, or 4, 4, 8. So let's just do, now we can do 2. You see, in this case, we can't do 4. Right? So here we can't do 4. Here we can't do 8. So we will just do 2, 2 pair. Please, we understand.
Yes, sir.
Okay.
Yes, sir.
Now, each of these boxes that we've done to, we will just simplify. So let's take this blue one here. For the blue one, if you look at it, which one is changing from 1 to 0? So you just find those that are changing, the variable that is changing from 1 to 0. When you look up here, this is P, here is V, this is P, here is V. So if you look at it, which one is changing from 1 to 0 or 0 to 1?
The
Yes,
V.
V. So that variable that is changing from 1 to 0, that variable is cleared, is removed. That means it's gone. Right? But the one that is not changing. So which one is not changing?
So, say,
Yes.
if you compare the two
W.
numbers, the one that changes is the one that you clear.
Yes, the one that changes is the one that you clear. If it's changing from 0 to 1 or even 1 to 0, you clear it off.
Oh, okay.
It is because you remember this rule. We said A plus A inverse is equal to 1. You remember?
Yes, sir.
And in this, in the main term notation, A is 1. A is 1. A naught is 0. So all of this will be 1. So it's gone. So we don't need A again. It's just 1. It's gone. That's why we don't write it. So if something changes from 1 to 0, we just leave it because it's gone. We don't need it again. Please, do we understand?
Yes, sir.
Are we good? Hello.
Yes, sir.
Great. So which one changes? V changes from 1 to 0. That means V is eliminated. Is that right?
Okay.
Then what is left? P is not changing. So P is left. And then W here on this line is still 1. It's not changing. So we will write W P because both of them are still there. Please, is that right?
Yes, sir.
Good. Then let's go and do the middle one. So in the middle one, what is happening? Which one is changing and which one is not changing? Yes, which one is changing?
The W.
W. So W is cleared, right? So we don't have W. But which ones are not changing?
P and V.
P and V. So P and V, they are not changing. W is gone. Then we come and look at the last one. The last one, which one is changing and which one is not?
The P is changing.
P is changing. That means P is cleared, right?
Yes, sir.
So what remains? Yes,
The WV.
WV. Right. So what it means is that R, the equation R, is equal to WP plus WV plus PV instead of this long one. Please, do we get it?
Yes, sir.
So that is a Karnaugh map, and that is why we like it. Please, do we understand?
Yes, sir.
Okay, great. Let's take another example. Any question before we take another example? Okay. In the absence of any question, let's take this example. A solar street light controller has 3 binary inputs. B is equal to battery is sufficiently charged. Let me put it here. So B is so a solar street light controller has 3 binary inputs. B is equal to 1 if the battery has sufficient charge. N is equal to 1 if it is night. L is equal to 1 if the ambient light sensor detects darkness. Now the street light is on. The street light on output is 1 only when it is night and the battery is charged. Please pay attention closely. The street light on output is 1 only when it is night and the battery is charged, or whenever both night and darkness are detected. Please, do you understand? So the question is that we are to construct the truth table, simplify the function using a 3-variable Karnaugh map. And that question is where more exams more. Maybe Karnaugh map equation into how you simplify. I'll just give you the practical question. You form the truth table, and then you simplify using the Karnaugh map.
Okay.
Any theory near. So let's solve this one. Let's go over it too. So we are forming the truth table B, N, L. All the time, write it in the order we give you the variables. So B comes before N, before L. So that means B is the most significant bit. So we have B, N, L. Then we have light on. So let me say on. Then here is 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Is that right? Okay, great. Now, he says that the street light on output is only when it is night and the battery is charged. So where do we put our, okay, so let me write the main terms too, so that we can all be on the same page. So we have, this is M hash. So we have M0, M1, M2, M3, M4, M5, M6, M7. So see what we have here. So he says that the output should be on only when it is night and the battery is charged. What min term does it correspond to? Hello.
M6.
Hi.
What?
So M6.
M6. Great. So M6 is 1. Or whenever both night and darkness are detected, both night and darkness are detected.
M7.
Hello? Both night and darkness are detected. NL, right?
Yes, sir.
When both NLs are 1, 1. So
M3.
where do we put it?
M3.
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 M3 is 1.
Yes.
Mhm.
So can you add M7?
Come again.
Can you add M7 to this?
Yes, M7 because both N and
What
S.
about M? What about M5?
5, N and L is not checked.
Okay, 1 0.
Yes. So you see 0 and 1. M5 is 0 and 1. So NL. Please, you understand?
Sir,
Yes.
why did we add the M7? Because the question did not say at least. And the M7 to us, three,
Oh,
all of them on.
Okay. That's a very good question. Now we add M7 because he says that whenever both night and darkness, when we come to M7, night and darkness is on. Night and darkness is on. Do you understand?
yes, sir.
Yes, sir.
Great. Great. Please, are we here?
Yes, sir.
Yes, sir.
Yes, sir.
Good. So the conditions are whenever light, it is when it is night and battery is what? Charged. That's N is 1 and B is 1. So here N is 1, B is 1. N is 1, B is 1. Then and both night and darkness are detected. So N is 1, L is 1. N is 1, L is 1. N is 1, L is 1. Please you understand? Then the
Yes, sir.
rest are all zeros. We don't need them. So we are going to write the main terms. So this is a truth table. When you do this, you are done. A. Please, when you're writing it, don't forget to include the M hashtag too. All the time include it. Now, the next thing is to form the Karnaugh map of this expression, be the K map. So how do we do it? We take, because they are the 3 map like this. Then what will I write on the 2 side? On the
NL.
NL grades. NL goes up here. Then B comes down here. If you miss the order, you get it wrong. The order is very, very important. You can't miss it. If you miss it, you get it wrong. So here is 0 and 1. 0, 0.
0, 1.
0, 1.
1, 1.
1, 1.
1, 0.
1, 0. Okay, so what do we have? We have M3, 0, 1, 1. So 0, 1 1. Where is 1 1? So 0 here. Let me just pick green. So 0 here, 1 1 here, so 1. Then we have 1 1 0, so 1 1 0 here. Then we have 1 1 1, so 1 1 1 here. Then we'll do the grouping. So in this case, the grouping is going to be 2. And we have this 1 2, so 2. Please, do we understand?
Yes, sir.
Yes,
What would
sir.
this one be? Yes, if you simplify it, what will it be? Yes.
NL.
NL for this one. Oh,
Oh, okay. That will be BN.
it will be B
N.
N. Then this one will be what?
NL.
Yeah.
NL. That means that the function on, which is B N L, is equal to BN plus NL. Now, if you build this thing in Proteus, it will work exactly the way we want it to work. But that is how I built that keypad I brought to class that it was working and you guys were shocked how it worked. This is how I built it. So Boolean algebra is very, very interesting and practical. Please, do we understand?
Yes,
Yes, sir.
Okay, let me give you one try before we close. It's almost 2 o'clock. So let me give you one practice question. Is that right? So let me find a difficult question.
Sir.
Yes.
Sir, with the Karnaugh map, I understand, but how to trace is a problem to me.
How to?
Trace it.
Mhm.
The W, like with the B and the NL. I understand how they got the BN and the NL, but how to trace it to get the answer? I'm confused with it.
Is it in the drawing of the map?
Yes. So
Okay.
you circled, you grouped it into two.
Yes. So it's either you are grouping it as two twos or you're grouping them as fours or eight. They are all powers of 2. So look at what happens here. But you understand how we eliminate them.
Yes, sir.
Your problem is with the grouping.
Yes.
Is that your problem?
Yes, sir.
Okay, I understand. But that thing myself, it was a problem for me until recently. So it's normal. When I started to teach, then I was learning it again and I was like, that thing was easy. Now Oh, okay. Then I got it. That's how learning is like. So there are many things you yourself you don't understand. You will learn them as you grow. So this is it. When we have 3 ones, there are two. Look, if I group only these two, let's say I'm grouping only um the down to only these. I'll be left with this standalone one. And the equation in that case would be Bn plus this one here, which is going to be you see the B there is 0, so that would be B bar because it's 0.
Yes, sir.
Then NL. Is this thing simplified? No, it's not simplified because you can use the absorption rule. We said that when you have A, you remember there is a rule we wrote in class. If you have A plus A bar B is equal to A plus B.
Plus B.
Yeah, so this is going to be Bn plus NL. So it's not simplified. You still have to simplify. That is why we don't leave. If you have another one, you can form another group. Just form that group with them. Just clear them off. If this box, if the Karnaugh map, right, rather look like this. Then let's say we have one here, one here, one here, one here. This thing, you can't simplify it. There is no way you can simplify this. Please, you understand?
Okay.
Is there a way you can do the groupings? So here's A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. There is no way you can simplify this. Because how do you group it? Are you going to group it this way? But you're in a puzzle. Yeah. Oh, somebody do puzzle. We can't group it this way. Please, you understand? Now, look at something. Let me just take you through some scenarios so that you will understand this thing clear. I should have even done this earlier. I'm sorry I didn't do that. So look at this. If we have this Karnaugh map, then let's say we have one here, one, one, one here. Let's say we have these. This one, okay, it's 2 o'clock. So this one forms one group. This one forms one group. I say we need to be an neighbor forming group. So it's alone. Let me say that here is T and UV. Then here is 0, 0, 0, 1, 1, 1, 1, 0. Then if you are forming the Karnaugh map, what would the expression be for this one? What will it be? Yes. Hello.
He said to be you.
It will be what? UV. Then what will
Yes,
be
sir.
the Karnaugh map for this?
Said to be TV.
It will be T.
T
TV. Excellent.
TV.
It will be TV, right?
Yes, sir.
Yes. TV, because U is changing from 0 to 1. It's V that is still the same. Then what will be this one? Yes. That one, do we remove anything?
None of them is changing.
No.
No,
So it's still the same. So what will it be? Yes.
TUV.
Are you sure? The T here is 0. So it's going to be T bar, U bar, V bar because they are zeros. Is that right?
Yes, sir.
Okay, if I give you a kind
Yes,
of
sir.
map that looks like this, how will you write it? So let's just practice more on that. You have a kind of map that looks like this. One like this. And let's say this is P, QR. And let's say that here 0001 111001. Then let's say that 1 1 1 1 1. How will it be like? I wish you can do the groupings yourself. So do the groupings yourself and then tell me the answer.
I think this one will be okay.
Yes. So what will you get? Yes. So what did you get?
The P bar Q bar
Okay.
plus PQ
Plus
plus
PQ
plus P bar QR.
plus
Mm,
P bar
P bar Q.
P bar Q.
Yes, sir.
Okay. Who else got the same thing or something different?
I'm getting all PQ.
You're getting what?
PQ.
Okay. Yes. Who else? Okay. Let's do it together. So how do we do this? This is one group. This is one group, and that is one group. That means that we are going to get three answers, right?
Yes, sir.
Yeah. So what would this one simplify to? Which one is changing and which one is constant?
The R is changing.
The R is changing, so the R
Yes,
goes.
yes, sir.
Right. So
Yes.
what will we write? Yes.
Okay, so you get
P
P
bar
bar,
Q bar.
Q bar,
P bar Q bar.
Q bar. Yes, sir.
How does
Yeah,
this one to look like?
yeah,
Yes.
there.
So that one, which one is changing?
The R is changing.
The R is changing.
R
Changing.
R is changing and
Yes.
Q is the same. So what will it be? Yes.
PQ.
PQ. What
Yes.
about this one? That one, which one is changing and which one is constant?
So this one, P is changing.
Okay. So what will it be?
It will be QR. But the R will be bar.
Q
or
Alpha. So the final expression will be P bar Q bar
Cuba.
plus PQ
plus
plus
QR bar.
QR bar. Easy is very simple.
Yeah.
Okay, let me give you one more to try. If you don't understand this, mondane. Timo pa monti asientem na mondantem. You know, ebe siri pe kosi se mo beti asemo. Maya margin se mo nti dia mechire monas. Okay, great. So let's try. Please, are you understanding? I really want you to understand this. But I want to ask you, so because the rest of the course depends on these things. So let's say yes, M N O. Then one. Okay, no wait. One 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 here. Then let's say that we have 0001 11 1001. Will you try your hands on this?
Okay.
Yes. Is it tricky? Okay, so what are you getting?
For the first group in the horizontal,
The
Mm-hmm.
getting
M
bar
bar
and bar.
N bar
So you have what? M bar,
N
And bar
bar
N bar,
plus
plus
N bar O bar
N bar, O bar,
plus
plus
MN
MN.
MN,
Yes, sir.
yes plus
plus
NO bar.
NO bar. Is that all?
Yes, sir.
That's what you all got. Is that what you all got?
Mm, yeah, I was confused with how to get the how do you call it? The N bar O bar.
So you were what? N bar,
How-
O bar.
Yeah, I was confused how you got it.
So N bar, O bar will be this one, right? So when we look at, sorry, it will not be that
The
one.
vertical
No,
aspect.
It will be the
the
vertical one.
vertical one.
Yes, sir.
Yes.
Vertical one.
So when you look at it, M is changing, so M is 0. But then N is 0 and O is 0. And when it's 0, we use the bar. So both of them are 0, so we use the bar. Do you understand?
Yes, sir.
Okay.
Yes, sir.
Okay, great. Now, you guys are correct. But then we can simplify this further. Look at what I will have done if it was me. This is what I will have done. You see, I told you that you can group them in twos or in fours.
Yes.
So this here to here is 1, 4 for me.
Okay.
Have you seen the trick?
Yes, sir.
Yes, sir.
Then this one and this one
Another one.
is 1 for me. So that instead of me getting 4 terms, I'll get only 3. So let's look at it. If you look at this big one, between this side and this side, let's take the horizontal going this way. Which one is changing? Which term, N and O, which one is changing?
N
N is changing from 0 to 1. So N goes. That
1
means we are left with what? O,
O.
right? So we are left with O.
Okay.
But is it bar or positive?
Says bar.
O bar. Then when we come downside to M is going, so M2 goes. That means what we have left is what? Only O bar. Is that right?
Yes, sir.
Please, you
Yes, sir.
understand?
No.
Yes. So when you look at this huge 4 columns that I've put here, NO is 0010. So N is changing from 0
One.
to 1. So N goes. What is left that is not changing is only what?
Oh.
O, which is 0 and 0. Is that right?
Yes, sir.
But when you come to the vertical side too, M is changing from 0 to 1. So M2 goes. So N is changing from 0 to 1. So N goes M is changing from 0 to 1. So M two goes. Then what is left is only O. And O2 is what? 0. So we just do O naught. Please, you understand?
Yes, sir.
Great. Then I'm going to take this one here. And that one would be the usual one that you do, which is what? M bar O is changing from 0 to 1. So N bar. So M bar, N bar. Then here too would be M. O is changing from 1 to 0. So M, N. Please, you understand?
Yes, sir. And sir, you can
Yes.
also take the one we solved.
Mm-hmm.
So you can take the M bar O bar, then N O bar, then you factor
Yes.
O
Yes.
out. So
Yes.
M plus 1 give you 1.
So you see that if you do that, you are going to get what we got here.
Yes, sir.
Have you seen it?
Yes,
Please,
sir.
you understand?
Mm.
So if you simplify this and this, you're going to get O bar. And you still get back to this. So if you get these ones, just if you look at it well, you don't need to go back and forth and solve it several times. You can just get it straight from the map. Then you go your way. Please, we understand.
Yeah.
Hello,
Yes, sir.
are we here?
Yes, sir.
Or you are tired and you are sleeping already?
Yeah.
Why
Yeah.
you sleeping?
Yeah. Most of you are tired. Okay, so let's end the call here so that you guys can go and rest. If you could try this for me. So just take a screenshot and then go and try them, and let's see how you're able to do it. Then, but before we leave, I want you all to go and subscribe to my YouTube channel.
We have it.
Oh, okay. Because
For
some of you
20
still
marks.
haven't subscribed to my channel. So, if you have, then so kindly take a screenshot and go and try your hands on these.
Yes, sir.
I'm working very hard to get you your handout with all of these information in it. In fact, if I don't get it to you, you won't get a handout that has this information that I am putting in it. So kindly bear with me. I'll soon be done.
Okay.
All right. Good night, guys. Well done for
Thank you, sir.
staying this late. Yeah,
Thank
you
you,
all.
sir.
Yeah. God bless you all.
God bless.